Welcome back. In this video we're going to be focusing on rational inequalities coming from polynomial inequalities, and we're going to notice the slight variations between the two. So let's look at this following example, a basic example. Given the function x minus 4 divided by x plus 2, determine when the function is greater than or equal to 0. So our situation looks like this. Okay, so one key difference with a rational inequality is that we have to examine the numerator and the denominator separately. Okay, so like before, if we have to factor the parts to find the zeros, we need to do that first. So I examine this polynomial, and they're both already considered factored. So the numerator, its 0 would be positive 4. And I still look at the inequality symbol to determine whether or not we have a closed or open bracket in our solution set, and we would say in this scenario that we have a closed. So now looking at the denominator and its 0. So we would look at x plus 2 is already factored, and we would say we have a 0 of negative 2. Now with the denominator and its zeros, these will always be open, because to say that we used a closed bracket means that negative 2 actually works for this scenario. And think about what negative 2 is. If I place negative 2 in, we get 0 in the denominator. So negative 2 is not even in the domain of the function. So how can it be in the solution if it's not in the domain? Negative 2 is a vertical asymptote on the graph. For that reason, any zeros of the denominator will always have an open bracket. Okay, so we have the zeros of the numerator and denominator. Sometimes it's going to take more work to get those, but here it was rather simple. So like before, we have our interval test, negative infinity to positive infinity, negative 2, positive 4, like we said, closed at 4, open at 2. And we have our interval test. So let's choose negative 3, 0, and positive 5. So we place negative 3 in, and we're getting a negative number divided by a negative number. Two negatives, when divided, result in a positive. When we place 0 in, we achieve a negative divided by a positive. And like we saw before, an odd number of negatives results in a negative quotient or product. Okay? So now let's try negative 5. Placing negative 5, or positive 5, we get positive, and we get positive, which results in a positive. And according to our inequality symbol, we desire the regions that are greater than 0 or the positive regions. So that would be our regions on the outside, making our solution set for this rational inequality. Our solution set would be negative infinity to negative 2, open bracket, jumping to positive 4, closed bracket, to positive infinity. Again, negative 2 is not included because it is a vertical asymptote. And throughout these examples, I'm actually going to label any vertical asymptotes that show up in my set. I'm going to label that, just so I know exactly why it's not included. Okay? So that was a basic example. Let's try another. So let's look at this one. Example 1. So let's solve this rational inequality. X squared plus x minus 6 divided by x squared minus 3x minus 4. And we want to know when this is less than or equal to 0. Okay, so again, we wanted to separate this into the numerator and denominator. But first, let's go ahead and rewrite this function as it's been factored. So x squared plus x minus 6, when it is factored, we get x plus 3, x minus 2. in our denominator, when it has been factored, we get x minus 4 and x plus 1. Okay. So we have our function and factored. So we now want to look at the numerator and the denominator. Again, zeros in each. So the zeros of our numerator are going to be -3 and +2. I'll add up your zeros of. Okay. And looking at our symbol, we would have both of these being closed. So now our denominator. So our denominator, we would have zeros of +4 and -1. Again, coming from the denominator, these must be open because both of these values are the locations of vertical asymptotes on our graph. So just like our initial example, having 4 zeros, let's run our interval test. We have -3, we have -1, we have +2, and +4. So let's select, say, -4, -2, 0, 3, and 5. So there's a lot of testing in this problem. Let's just go through this one and one. So when I place -4 in, we're getting, let's see, negative, 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 negative. So an even number of negatives results in a positive. Placing -2 in, we get positive, negative, negative, negative. So 3 negatives, an odd number of negatives, results in a negative still. Placing 0 back in, positive, negative, negative, positive, 2 negatives, 2 positives, results as a positive. Placing 3 in, we're getting positive, positive, negative, positive, and placing in +5, we should get here a positive, 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 positive. Yep. Okay. Now something I just kind of skipped over is exactly what kind of brackets do we have with each of these values. So at -3 we say closed. At -1 we said open because that is a vertical asymptote. At +2 we said closed, and at +4 we said open because it is a vertical asymptote. So we desire, according to our symbol, we desire the regions less than 0, which were the negative regions. Making our solution set. -3, close bracket, to -1, open, jumping to close bracket 2, to open bracket 4. Alright, so highlighting just some of the key differences, the main is the denominator, how regardless of what our inequality is, they will always be open brackets because of them being vertical asymptotes on the graph. Now, one more example, since we kind of have the basic rundown of this type of problem. One more example for this video, for this lesson. Let's look at this scenario. x5 divided by x plus 5 plus 3 divided by x minus 1. So you might say we have two rational functions and we just look at them separately. In this scenario, with this type of problem, we must write this as a single rational function. Okay, we must, if it's not already. So we have, looking at this, we have a least common denominator, I would say, of x plus 3 and x minus 1. Okay, so x plus 3 I would multiply by x minus 1. Okay, and then with this, the 3, I would have to multiply by x plus 3. Now, unlike with us solving rational functions, finding least common denominator, where we disregarded the denominator, we just didn't write it, we need to include it here because it is going to affect our solution set, as we saw in the previous examples. So we need to have this here still. So we have this. We can simplify it, and when we simplify it, we get 5x minus 5 plus 3x plus 9 leading us to this simplified rational inequality. I'm going to pull a 4 out because there's a common term. When I pull a 4 out, I get 2x plus 1, and I still have x plus 3, x minus 1 in the denominator. So it has been factored. Now looking at the zeros of the numerator and denominator. So the zero of the numerator would be -1/2. And examining our inequality, this would be an open. So our denominator, we'd have zeros of -3 and +1, open. So we have our zeros, the 3 of them, and we are ready for our interval test. So our interval test would look like, let's see, -3, -1/2, +1. Let's choose, say, -4. We can use -2 here. We could use 0 in this region, and +2. So we place these back in. So again, we're looking at this form of our problem because it is a factored form. So place -4 in, we're getting negative on top, negative, and negative. So 3 negatives remain negative. Placing -2 in, we're getting a negative number, a positive, and a negative. Placing -1/2 in, or actually placing 0 in, sorry. Placing 0 in, we get, see, positive, positive, negative. Placing 2 in, and we should get all positive here. Positive, positive, positive. Alright. And each of our zeros were open. And we have a solution set. I'm thinking I haven't even looked at the symbol yet. So we have less than 0, so that would be the negative regions, and there, and here. Giving us -infinity to -3, open, jumping to -1/2, and +1, both open. Now out of our bounds, -3 and +1 are both vertical asymptotes. So again, we have our solution set. We have vertical asymptotes that kind of define what the solution set can be. But that is essentially how we go through a rational function, whether it's split into 2 and we need to make it one rational function, or if it's already put together. So before coming into class, I would like for each of you to take the time to solve this problem. given this function, determine the values of x for which make the function greater than 0. So as you end the video, take the time to solve this problem. The solution can be found in the notes, and like always, post your questions, comments in the classroom, and we'll try to get those questions answered before you come into class.